Okay, we're going to do 1.5, and 1.5 is really just training you how to look at derivatives in separate quantities, and it's looking at, let's say you have a complex function like this, and it's just kind of saying that you will reach the same conclusion by looking at the whole function as you will as breaking it down into its components. And it's using certain rules. And the reason it's doing this, because you're going to look at it and say, oh, this is kind of stupid, is just kind of teaching you to look at derivatives as separate when we break them down. We'll get to that soon enough. It seems clear that as x gets close to 2, we can see that 3x squared gets close to 12, 4x gets close to 8, and that the whole thing gets close to 19. Well, properties limits are showing you that whenever we have a limit of a constant, like this number minus 1, the answer will just be the constant, which is why we just subtract 1 from our result here. When we're approaching a limit where x approaches a, the answer will always just be a. When we have a limit where we're adding two functions or subtracting them, you can find the limit of one and add or subtract whatever was happening of the other, and you'll get the same answer. When you have a limit of a function that's being multiplied by a constant or a coefficient, you can just find the limit inside and then multiply by the coefficient and get the same answer. And when we have the limits of finding two functions multiplying each other, you can find the limit of one, find the limit of the other, and when you multiply them, you will get the same answer. Same goes for division. You can find the limit as for one divided by the limit of the other. You get the same answer provided that this limit doesn't reach 0, because obviously division by 0. And finally, this just says that any rational value of anything with an exponent, you can find the limit within the exponent. We'll get more to that in a bit. They're just teaching you to break it down into the components. So in this one, they break it down into finding the limit of 3x squared as x approaches 2, and then that as x approaches 2, and this as x approaches 2, which will just be minus 1 because it's a constant. And they show you that it becomes 12 here, 8 here, and minus 1 and 19. You might look at this and say, well, why? Why don't they just plug it in and solve it? And you're right. They're trying to get you to analyze things on an individual component basis, because when we reach derivatives, you're going to have to break things down. Okay? So they're doing it again here. We have a big function divided by a big function, and they're doing it twice. They're going to show first we can find the limit of this divided by the limit of that, and technically you could then break each of these down into their components, which I'm surprised they didn't. Well, they kind of did, because they just repeated what they found up here. And then you could also break this down into its individual components and then divide them, and then minus 2. And you might again say, well, why? I can just plug in minus 1, solve up here, solve down here, divide, and come up with minus 2. It's a lot faster. Yeah, and in some cases, in science, one of these components is not going to give you the right answer, the needed answer, or you're not going to be able to conclude. You're not going to be able to substitute and just find the answer. You're going to have to do a lot more manipulation of the equations. And that's what they're trying to teach you. Again, this one you might say, well, this one's not hard to figure out. I just throw in 5, solve for this, and get their same answer. What are they trying to show me? They're trying to show you, to break down each thing where you see x into two different limits and solve the limits individually to come closer to your conclusion, especially when you're missing data. And then they're going to teach you strategies. For instance, this one, we can't solve it when x is 3. There's no way we can just put x in. This is the example of substitution doesn't work. So you're going to learn when you can't substitute, look at factoring strategies. So it turns out the top here has 2 factors, and the bottom and the top can then cancel. And now we can see that we can substitute. We're always trying to reach a point where we can substitute in x. When we put x in here, we can see that it approaches 4. So that means up here, as x approaches 3, even though it's not solvable, the limit of this whole thing will indeed approach 4. Even though there's going to be an empty hole at 4, it still has a limit. Same with this one. We can't put 0 in here, but we're going to learn why we did conjugates before. If I multiply by the conjugate, I'm not changing the fraction, because I'm just essentially changing the denominator. I'm able to resolve the top, so there's just x, and then I have something to x times this thing at the bottom. The two x's can cancel, And that's what I was trying to do. I was trying to get rid of this x at the bottom. And now you might say, well, you still have x at the bottom, bonehead. But it doesn't matter, because when x is 0 here, this still comes out as a whole number. So when x is here, I get 0 here. I get square root of 1, which is 1, plus 1, which is 2. So I get 1 over 2. So it's solvable now that I got rid of this multiplying x. This was the x I needed to get rid of. So you can see that even though you can't visually substitute up here, we can use a conjugate strategy to come with a solution so that indeed, when we graph this, we will discover that we approach the y values of a half for this graph as x approaches 0. And this is an alternate strategy for factoring, and it's a very important one that I'm going to get to in this example. Okay, and this is really hard to understand. So you're going to have to, and I'm going to do it right now actually, because this is a really tough one to comprehend, but he's going to have it on your test. Okay? You're going to have a situation where you have a function that can't be solved, substitution, and visually, you're not going to be able to figure it out. Okay? You can say, as x approaches 0, I can't just put a 0 in here, but up here, oh boy, I hate that. Up here, I also can't solve anything. I don't know what to do up here. And this is a specific technique, and you do more of it in university, but we're going to replace this whole thing with a value that this means cube root. And if you don't know that, you'll need to study your exponents more. This just means the cube root of something, and you're used to just square roots, which is something times it's something. So if I had the square root of 9, all they're saying, what number times itself is equal to 9? 3. Well, cube root says, what number times itself will equal to the thing in here? So in this case, 2 times itself will be equal to 8. And guess what? You can have cube roots of negative numbers. Why? Because minus 2 times minus 2 is plus 4, times minus 2, again, is minus 8. So cube roots, 5 roots, 7 roots, 9 roots, you can have a minus number in there. Even roots, like square roots, or quartic roots, or 6 roots, or 8 roots, you cannot have a negative number in there. Interesting. So there's no way to find the cube root of this. So I'm going to replace it with my imaginary number that I can cube root. What can I cube root? Well, anything that's cubed. So I'm going to make u equal x plus 8. But that means if I'm going to replace x up here, I need to replace it down here with something. And if I rearrange this, I also realize that x is equal to u cubed minus 8. So these two terms are useful. Can I just do that? Yeah, you're allowed to substitute and replace so long as you don't break the rules of math. And here's the rule of math we're breaking. We used to be looking for when x was approaching 0. So we're looking still for when x is approaching 0. But that means our whole u, what u approaches, is different. Why? Because u does not equal x. It's equal to x plus 8. So as x approaches 0, maybe I should put it in this top one. I'm just going to make a copy of this. When x approaches 0, which is what we're looking for, this becomes 8. U cubed equals 8. What is u when u cubed is 8? U must be 2. If it wasn't solvable, u would be the cube root of whatever's in there. But u in this case is 2, because 2 times 2 times 2 is 8. That means when x is approaching 0 for this thing, u is approaching 2. That's important for you to solve. So when you're trying to figure it out, just put a 0 in this, and then solve for u to see what u is approaching. And that's probably the hardest part that students have with it. So we're no longer looking for the limit of something of x approaching 0. We're looking for something as u approaches 2. And what can I replace this in the bracket with? Wherever I see x plus 8, I'm going to put u cubed. So I'm going to put this whole thing, I'm going to replace with all the values. I'll just put it over here, that I just found. So I'm saying I'm replacing u plus 8 with a mystical value of u cubed. And as I discovered, I'm going to replace x with u cubed minus 8. That's because I can't have two variables in here. So when I replace x with x up here, x plus 8 with u cubed, I must replace the x with something. Great. Well, this is solvable now. Let's solve it. What's the cube root of something cubed? It's just whatever's in there. So I get this up top. And I get u cubed minus 8. And you might say, well, I still can't put 2 in there, buddy. It still reaches 0 down here. Fair enough. But now, this has a cube root. If you don't remember your cube roots, and now right at this very moment, I do not, oh, actually it has it in the bottom left. Look it up on the internet. So this has a cube root of this. And go up, look at the difference of cubes. That's what you're looking at. Because this has a cube root and this has a cube root. So we have a difference of cubes, which means I can factor out this and I'm left with that. Look it up, Google difference of cubes. Now, I always say if you have something in the bracket that's being subtracted and something that matches down here, and down here they're all multiplying, I can cancel out this entire bracket. Because it's this divided by this multiplying that. Well, this can cancel out. So I'm left with this at the bottom. Well, now, remember, I'm looking as u approaches 2. So I'm looking for, I'm just going to replace u with 2 down there. And I get 4 plus 4 plus 4. I get 1 over 12. Which means that for this equation that I started with, as x approaches 0, the limit is 1 over 12. And I had to solve it using solving fictional u as u approaches 2, but the limit is still going to be the same limit because I still obeyed the laws of math when I substituted it. So you can see down here that the limit as x approaches 0 is 1 over 12. This is the hardest one you're going to have to remember. And then this one is also interesting, and I'll have to say this is the second hardest one you're going to have to remember. And this is going to be logically. The absolute value graph is probably one of the most illogical graphs we do. And that's because it doesn't really make sense of why we would take a positive value. But I want you to imagine a line. I want you to imagine this line that we take all the time called y is equal to x. Y is equal to x. And I want you to imagine what are all the y values down here. Well, they're all negative, right? They're all negative. Absolute value says I'm going to take only positive values of x. So what happens to this line down here? Well, it gets bounced up here. All these y values that were minus 3 become plus 3. So I get 3 comma 3 up here instead of 3 comma minus 3 down here. So really an absolute value graph is the same as whatever its normal graph is inside here. But when it hits negative values of y, those y values suddenly are turned positive. So that's one way to look at it. So that means if I'm looking at an absolute value graph, if I'm looking at just a normal absolute value graph, the right side, so I'm looking at y is equal to absolute value of x. This right side, for when x is bigger than 0, or equal to 0, it's just y is equal to x, just like my line, right? And this left side is the same as my line, but whatever I solved in my line, I'm going to multiply by negative, because remember, these negative 3 values used to be down here by y. So once I solved x here is 3, if I multiply it by, or for x of negative 3 right here, when I multiply by minus, I get a positive 3y. So this left side is like taking the negative of whatever's in this. It's like taking whatever's in this and multiplying by negative 1. If you don't believe me, take a bunch of x values and plug it into this, and take a bunch of x values and plug it into this, and then plot it, and you'll see you have an absolute value graph. Well, it turns out this also works for more complicated absolute value graphs. So if I have the absolute value of y is equal to x plus, we'll say x minus 4. Okay, and I'm going to get rid of this absolute value here because it's clearly not the same. Well, this absolute value graph here has a pivot point here at 4 comma 0. So when x is 4 comma 0, over here, I have a normal line, and normally this line would go down here. But on this side of the graph in black, it's the same as minus and then times whatever's in my absolute value. So this side of the graph is actually this function, and this side of this graph is just the normal, what's in there, the normal line. We can use this to understand the rates of change of, or limits of a function. So everything to the right of the vertex is just going to be what's in there. And everything to the left of the vertex is going to be another line formula of a minus times the bracket of whatever's in there. And that's what they do here when they're evaluating this function. This function's impossible to evaluate because of the absolute value here is hard to decipher in terms of what's going on here. And we're looking for it as x approaches 2, right? All right. They're asking us to evaluate the limit. Does it exist? And here's where it doesn't exist. Here's how you prove it doesn't exist. So I want you to take the right side of the graph, and I said the right side of the graph. So we're going to say, where's the vertex, by the way, up here? The vertex is at 2, right? So we're going to take the right side of the graph, and we actually don't even need the bottom. The only reason they include the bottom is because it's not solvable that way. And so we're going to take one side of the graph, and we're going to just treat the top like the normal line, divided by this. And we're going to take another side of this graph to the left of the vertex, and we're going to treat it as minus 1 times whatever's in the brackets up here, all over, since the other thing doesn't have an absolute value, this. All right. It's quite easy to see that when these cancel out, I'm left with plus 1, and then when these cancel out, I'm left with minus 1. Interesting. Okay. Let's just take values of x as we look at some values. Let's approach x is equal to 2 from the right side here. Let's take a 3. So when a 3 goes in there, I get 1. When a 3 goes in there, I get 1. So I get plus 1 divided by plus 1. My value is plus 1. Now let's take values of 3 down here and 3 down here. Oh, no, sorry. Now, yeah, so now as we get closer and closer, if I took 2.1 on this side, I get 0.1 divided by 0.1. Still comes out plus 1. So I can see my limit as I'm approaching 2 is 1. Now we're going to approach the 2 from the negative side, my bad. So we're going to take negative 3. So when we take negative 3 here, I get negative 3 minus 2 minus 5 times minus 1. I get positive 5. But when I take negative 3 down here, I get minus 5. Plus 5 divided by minus 5 is minus 1. Then when I get really close to it, like negative 2.1, I get positive 0.1 up top and negative 0.1 at the bottom for, again, a result of negative 1. If I was to graph this, I can see that the bottom to the left of this graph, before x is 2, right there, is a minus 1. And I can see that the right side of 2 of this graph is a plus 1. And I can just put a 0 there. So I can see that as I approach the vertex, or sorry, the x is equal to 2 of this function, it's always approaching minus 1, whereas I approach from the right, it's reaching plus 1. Therefore, there is no limit at x as x approaches 2 for this function, because I'm approaching 2 different values. For you to evaluate this, you have to understand that the right side of this graph, because it's the vertex, is going to be like the line, and the left side is going to be like minus 1 times the inside. And that's hard to grasp. Another thing to realize about absolute values is when you're studying it more, you can replace it with this, because when I square x, it becomes positive, and then when I square root it, it's going to be still positive. So this square, and it's going to result in x. So by doing a square root, I'm essentially doing an absolute function. And that's what an absolute function is. It's squaring it and then square rooting it to keep it positive. And you're going to learn to use this later on as well. There's the result of the limit for that we just talked about. And then this one. Explain why this doesn't have a limit. Well, you're going to discover that this is like a half circle as they draw here. And as we approach 3 from the negative side, right here, we have a 3. But as we approach 3 from the right side, it doesn't exist. There's no values of 3 on the right side of 3. So it doesn't have a limit. See, it does not exist because the function's not defined on both sides of 3. That's the answer. So you're going to hit situations like this. Same with the root function that I described. So there's only a function. If it's a polynomial function, then the limit is whatever can be substituted in. And then they give you the strategies. Direct substitution, factoring, rationalizing, one-sided limits, change of variable. That's what we did with u cubed. The answer, do I even want to bother answering this first section? This first section's pointless. The answer is yes. There's a difference. As this approaches 2, it's not at all the same as the... Oh, is it? Let's see. Is this a 2? 5, 5, and 5. So I would say these two are the same. For this one, yes, because you're only doing limit as it approaches 3, and then you're adding x. So you had to have a limit approaches 2, x2 for this one as well. So this one is not the same. This one is the same because commutative properties say I can rearrange it any way I want. But because they rewrote this here, this one here, with just the limit applying to 3, they had to rewrite it here as the limit approaches 2 for this x value. So this one is not valid at all. How do you find the limit of a rational function? You've got to use a conjugate method, or if substitution doesn't work. Once you know the limit of x approaching a from the right side and x approaching a from the right and left side, do you know the limit? Yes. You know whether it exists or not. And if they don't, they're either going to give you the limit or that it does not exist. So yes. Evaluate each limit. So here you just substitute, right? Because you can. So you get 6 over 6, 1. And here it's approaching 2 pi. So you just put 2 pi in there and you evaluate the limit. So you get 8 pi cubed plus, what's 2 pi? So you get 2 pi cubed minus 5 pi cubed. So they're all cubed. So they're all apples. 8 plus 2 is 10 minus 5. You get 5 pi cubed. That's the answer to that. What about this one? Well, this is just substitution. See, because this is a polynomial, you can just substitute. You can just solve each individually. So minus 1 squared is going to be plus 1. That's going to be minus 1. That's going to be plus 1. So you're going to end up with plus 1. As it approaches 0, do we have a problem here? No. Square root of 1 is 1. And 3 plus 1 is square root of 4. So it's going to approach 2. So there's no problems when you can substitute 0 in a denominator. As it approaches 9, do we have a problem here? No. Square root of 9 is 3 plus 1 over square root of 9, which is the third. So you get 3 1/3, which is 10 thirds. And then when you square it, you get 100 ninths. And that can't be simplified. So that's the limit. What about this one? Do we create any negatives? Yes, we do. So this one's has no limit. Because when we get a negative 3 up here, we get negative 6. We get a negative, oh, no, hang on. We get negative 3 here, we get negative 6 plus 4, so negative 2. The negatives become positive, we get positive 3. So this does have a limit. Graphing this would be interesting, and you can also solve it. You can see why that section was kind of a waste of time. Using a graphing calculator, so just use Desmos. And for those of you that don't have a computer at home, and I don't blame you, things are tough when you don't have a computer at home, there are excellent loan systems. There are people online that can also find you a laptop for free, and schools lend. So don't ever give up. Like, use all your resources. So obviously we got a problem here. Okay? We've got a problem in that we have what's essentially going to be a weird parabola, but at x is equal to minus 2, we have an asymptote. But fortunately, they're saying use a graphing calculator, so you can just plug it in and see. But you can see that substitution in this, oh, actually substitution in this, I got it wrong. There's no asymptote there. The asymptote is over here at +2. And so we're going to have this weird, and there's another one. Actually, the other one's going to be vertical or diagonal. So you're going to have this weird stretch thing here and this weird stretch thing here. And yeah, it's probably going to be more like that. There we go. It's more what it's going to be like. It's going to be like that. And that's going to approach it like that. It's going to look very strange. And you can see when it's -2, we get -4 down here. And when it's -2 up above, we get -8. So it's going to be approaching 2. Which means when you do graph it, whatever it is, the value of y is going to be +2. And then when you substitute here, you get 2 over square root of 2, which is going to be just this, 2 over square root of 2. It's roughly, 1.4, something like that. If you want 2 is the same as square root of 2 times square root of 2, cancels out. You're going to be left with the square root of 2 as the answer, 1.41 something. When you graph this, it's going to look interesting. You're going to discover that this can't have values. Oh no, this can have any value, but it's always going to be positive. No, for x values are negative, you can have negatives. I don't know what this is going to look like, but Desmos is interesting. Prove this. They want you to prove this. So as t approaches 1, as t approaches 1, prove it. Well, you can just prove it with substitution, or you could prove it with graphing, where you're going to get 1 minus 1 minus 5 up top, and you're going to get 6 minus 1 at the bottom. So up top, these cancel out. You're going to get minus 5 over 5 and minus 1. Not quite sure what they're trying to make you prove there. Maybe you can do the limit of each of these separately and show it that way. Not quite sure what they're trying to prove. It is going to have a horizontal, vertical asymptote when t is equal to the square root of 6, or 2 times square root of 2. No, square root of 6, sorry. When t is equal to the square root of 6, this becomes 0. Evaluate. Okay. This you have to use factoring and conjugate. Okay, and they want you to practice it. So you cannot evaluate that. It's impossible. But up top, let's just rearrange both of these the way, well, you're going to have to realize that's still a difference of 2 squares. So that factors out to 2 plus x times 2 minus x. If you can't see it, go look it up on YouTube, over 2 minus x. So it will indeed factor out, and when x becomes 2, the limit will be 4. This is a case where you have a hole, but you're going to be left with like a straight line. And there's just going to be an indeterminate value there. And that's what happens when you cancel out. You create a hole. Go revisit your functions. This is also clearly going to be a factoring issue. And when I look up top, you have to remember that I'm looking for a number that multiplies out to 6 and adds up to 5. So we're talking about 2 and 3. So you can do it x plus 2, you can't stop like this, and x plus 3. You have to divide by 2 and divide by 2. So I'm going to see that it's x plus 1 and 2x plus 3. I'm just making sure that's 2x squared, that's 3x plus 2x plus 3. So that's accurate. All over x plus 1. It was pretty sure I was going to find a cancellation. And I'm left with 2x plus 3 up top. Now, as x approaches minus 1, I can substitute, get minus 2 plus 3 plus 1 is the answer. So as x approaches minus 1, this whole function approaches y is equal to 1, but there's going to be a hole in the line. It's going to look like a line, by the way. Let's see. Difference of cubes. So there's where you got to punch. I should have difference of cubes memorized, but there's also a difference of cubes when they add and a difference of cubes when they subtract. So here we go. There's when they add, there's when they subtract. Sum of two cubes and difference of cubes. And in the books, they always like to give you the difference of cubes. So just keep it written down somewhere so that you don't have to do it. So we can see our top value is going to be just it's going to be this, x minus 3, and then it's going to be this, x squared, plus, plus, it's going to be the opposite, plus 3 times x, plus 3 squared. And if in doubt, you can expand it, and you should get that. All right, it's pretty clear that I can cancel, and I'm just left with this at the top. And now, when I substitute 3, I don't have a problem anymore. I get 9 plus 9 plus 9, 27. So that means the limit of this graph, which is going to be a parabola with a hole in it, is 27. But at the spot 3, 27, you're going to see a little hole. If you punch this into Desmos exactly as is, it's going to draw you a parabola, and there's going to be a hole at this coordinate, 3, 27. Okay. This needs conjugates. These all need conjugates. How do you get rid of the top? And you might say, well, I'm not trying to get rid of the top, I'm trying to get rid of the bottom. But you'll discover when you solve the problem at the top, you'll solve the problem at the bottom. Whenever you're changing a fraction, you can multiply by 1. And since we also know that when we multiply a square root by its conjugate, it disappears, and that's its conjugate. Since this is still 1, and this is still the conjugate of that, we will get rid of it. So we get 4 at the top minus whatever's in the bracket. 4 plus x in a bracket. And on the bottom, just leave your x there, and just leave it multiplying the conjugate in a bracket. And you'll see why in a second. Just leave it alone. Up top, you're going to see it's going to be 4 minus x. 4 minus 4 is 0, but you're left with minus x. How did that x become minus? Because when you expand it, it's going to be minus times the whole bracket, and that minus is going to affect both terms in the bracket. Right away, I can see my x's canceled, so I'm left with minus 1 up top, and I'm left with 2 plus the square root of 4 plus x. Now, you might immediately say, I still have an x in the denominator, and I can't make x 0 in the denominator. Yes, you can, in this case, because it's being added to 4. So when x is 0, that's what happens. Well, it's clear that I see a minus 1 over 4. So that means the answer to this question as x approaches 0 for this limit here, not this one here, it's minus 1 over 4. The y value will be minus 1 over 4. We're going to see a weird, will we see a half root? Some weird half root? I don't know what the graph will look like, actually. I shouldn't speculate. And you're going to discover these are also solved with conjugate. So I'm going to multiply the top and bottom by the conjugate, and treat this like it's in a bracket. And when I multiply the top by the conjugate x minus 4, that's because this times itself becomes x, and this times itself becomes minus 4. All over, and just keep the x minus 4, and you can see y immediately, times the square root of x plus 2. And you can see that these cancel out, and I'm left with 1 over the square root of x plus 2. And when x becomes 4, that's what I get, and it becomes positive 1 over 4. So that means the limit of this as x approaches 4 is 1 over 4. Please continue with that. The conjugate rule still applies to this. The conjugate of this is still square root of 7 minus x plus square root of 7 plus x. And these top things will still solve themselves. Please do some yourself. I should not be solving all of them. I'm just trying to show you for the first couple. Okay, now I'm going to use change in variable. Yeah. So always be aware. Actually, these are helpful to do. I don't think I've done them in a while. So I'm going to show you what you're going to be changing your variable. Always be aware that whatever's in the cube root is what you're going to be changing. Okay? So in this case, you're going to make x is equal to u cubed. Okay? And this allows you to realize, well, when x is approaching 0, I'm still looking for u. Oh, as x approaches 8, I'm still looking for u approaching 8. Oh, hang on. No. You put 8 here, and u cubed. So now I'm looking for u approaching 2. Because you put the 8 of what you're looking for here, and then you solve for u to figure out what it's approaching. So that means I'm no longer looking for x approaching 8, I'm looking for 8u approaching 2. And wherever I see an x, I'm putting in u cubed. I'm putting u cubed. And you'll see why in a second. Now, at the top, what's the cube root of u cubed? It's u. And you might say, I still can't solve it. You didn't help me. Yep. What's going on at the bottom? Difference of cubes. I hope I have my difference of cubes memorized now. It's u minus 2 times u squared minus, no, plus 2u plus 4.